Hi, my name's Andrew, and I'm a junior in CIS studying artificial intelligence. Um, my research project was about optimal neural network depth for forecasting noisy signals. You could think about it as if you're a deep learning practitioner trying to forecast energy demand. You want to forecast the next 200 days, given the past 800 days. What type of neural network architecture would you begin with in your prototyping stages? So we sought to determine what is an optimal depth of a neural network that performs the best for forecasting these signals. The experiment began with generating our noisy signals. Each noisy signal is composed of 10 randomly generated sine waves, so amplitude, frequency, and shifts are all uniformly sampled and combined. So that's this top signal here. And then we introduce some noise based on different signal to noise ratios. And the noise is generated from a Gaussian sampling process. And we combined it into this noisy signal down here, the third one. So the task of our model is to, given the first 800 time steps of a noisy signal, forecast the next 200 time steps of the clean signal. And we did this by creating 10 different neural network models, each sharing the same feature extractor, which was a convolutional neural net with a kernel size of 1 by 5 because we have 1D signals. And we fed the output of that feature extractor into our fully connected networks. And we had 10 different fully connected networks, each with different depth here. This layer times n, and n varies between 1 and 10. And we just trained each model on each signal to noise ratio data set 3 times and averaged the score to get our average loss for depth. And here are some cherry-picked predictions of models to just demonstrate the purpose. So here we have the blue inputs and also the blue target signal, and the red is the forecasted signal. And our loss function was an MSE loss to compare the two and train. So for a signal to noise ratio of 4, performed decently, and same case for 0.25. Bear in mind, these are cherry-picked signals, so there were some ugly forecasts. And our results were, this is a normalized loss function graph. Results were that neural network depths of up to 5 layers performed decently well. And then there was a strong increase in loss from 5 to 7 layers and then a plateau. So this was initially surprising because I thought deeper networks generally perform better than shallow networks for many deep learning applications, but turns out not in this case. Our best performer was a network with 1 layer. I'm not really sure why, but that would be something further to research into. Some implications are, if you are a practitioner forecasting noisy signals, such as I mentioned, energy forecasting, you would want to begin your prototyping with shallower models instead of going straight to deep models, because deeper models have longer training times. You'll waste more resources computationally. So yeah, good to save energy with shallow models. Thanks for listening.